The ground shook before the men heard anything. That was always how it began, a tremor traveling upward through 1,200 feet of packed earth and fractured rock, through the timber supports in the seam walls, through the boots of men who had learned to read the language of underground pressure the way a sailor reads wind. It is 1842. The pit is called Huskar Colliery, Silkstone, West Yorkshire. The shaft descends at 40 degrees into a seam of black bituminous coal 31 inches thick, barely enough space for a grown man to lie flat. The men who work this seam are not always men. Some are 9 years old. Above the pit mouth, 300 yards from where the shaft opens into cold English air, a steam engine sits on a bed of mortared stone. It weighs 11 tons. Its boiler operates at 40 pounds per square inch. The engine drives a winding drum that hauls coal to the surface, and on that drum depends everything below: ventilation, haulage, the speed of ascent and descent, and, at the critical moment, the margin between survival and collapse. The engine does not know it is killing anyone. It converts heat to motion, motion to work, work to profit. The mechanism does not distinguish between a shaft full of coal and a shaft full of children. It applies force according to the pressure of steam and the tolerance of iron. The human bodies arranged within its mechanical logic, the families at the pit mouth, the ledgers in distant offices, these belong to another category of concern entirely. But the engine did not arise from nowhere. It arose from need, from desperation, from genius, from the intersection of a dying industry and a man standing in a Glasgow workshop in 1765, staring at a model Newcomen engine, realizing that the machine was wasting 70% of its energy heating and cooling the same chamber over and over again. What he fixed would feed empires. What it cost would take generations to name. There is a particular kind of progress that does not announce its cost at the moment of its arrival. It arrives as light, as warmth, as the sound of looms running through the night in mill towns that had never known continuous production. It arrives as cheaper iron, faster ships, grain moved inland along rail lines that did not exist a generation prior. It arrives as population growth, expanding cities, the slow extension of life expectancy among those who could afford to live inside its benefits. The steam engine arrived this way, and yet beneath every mill, beneath every forge, beneath every pumping station that kept the floodwater from drowning the lower seams, beneath all of it was coal, and coal required men, and men required descending. This is the central paradox of the Industrial Revolution. The engine that liberated human labor from its most brutish physical limitations simultaneously concentrated a different population, poorer, younger, geographically isolated, into conditions more dangerous than anything the pre-industrial world had routinely produced. The question is not simply what the steam engine built. The question is what the steam engine required. Because requirement is where the accounting becomes honest. Requirement is where the 11-year-old boy hauling a tub of coal through a seam 30 inches high appears in the ledger. Requirement is where the ventilation failure, the boiler rupture, the cage dropped by a snapped chain enters the record not as accident but as cost, anticipated, calculated, and deemed acceptable against the margin of production. The engine did not create human suffering. Suffering preceded it by millennia, but the engine organized suffering, scaled it, made it regular, systematic, and invisible to those who owned the machinery. That invisibility is what this history refuses. By the middle of the 17th century, England was running out of wood. This is not a metaphor. It is a measurable, documented fact recorded in timber surveys, naval requisition ledgers, and the increasingly panicked correspondence of ironmasters who could no longer guarantee fuel supply for their furnaces. The forests that had fed English industry, the charcoal forests of the Weald, the ancient woodlands of the Forest of Dean, had been reduced by centuries of unregulated cutting to a fraction of their former extent. A country that had built its naval supremacy on oak was watching its shipyards slow. A country that had smelted iron for 300 years was watching its foundries go cold. The crisis was felt in the price of bread, in the cost of heating a room through winter, in the slowing of iron production at the precise moment that European rivals were accelerating. Sweden controlled the highest quality bar iron in the world. The Dutch controlled the Baltic trade routes. England, sitting on the largest accessible coalfields in Europe, was losing ground. Coal was the answer. Surface deposits had been worked in Northumberland and Durham since the 13th century. By 1700, London was consuming 400,000 tons per year, but surface coal was nearly gone. What remained lay deep, 30, 50, 100 fathoms below the surface. To reach it required shafts filled with water. A single deep mine might require 50 horses in continuous rotation simply to keep the lower seams dry. The cost consumed profit margins entirely. That wall held until 1698, when Thomas Savery patented the miner's friend, a steam-driven pump limited to lifting water 25 feet. For mines descending 100 fathoms, it was useless. Thomas Newcomen improved upon it in 1710 with a piston and cylinder design that worked. By 1729, 100 Newcomen engines operated across Britain. The mines went deeper, and as they went deeper, the men descended further from air, further from rapid escape, tied to a machine above them they could hear but not see, and upon whose operation their lives entirely depended. James Watt was not trying to change the world. He was trying to repair a model. In the winter of 1763, Watt, a mathematical instrument maker at the University of Glasgow, was handed a small working model of a Newcomen engine for repair. He fixed the mechanical faults. Then, with the disposition of a man who cannot leave a problem alone once he has seen it clearly, he began to calculate. What he found was damning. The Newcomen engine wasted the majority of its energy repeatedly heating and cooling the same iron cylinder. 3/4 of every pound of coal burned was producing heat that vanished into the atmosphere without moving anything. Watt's solution, arrived at during a Sunday walk across Glasgow Green in 1765, was mechanically revolutionary. Separate the condensation from the cylinder entirely. Keep the cylinder permanently hot. Condense the steam in a separate, permanently cold chamber. The separate condenser. It sounds simple. The implementation consumed 11 years and the financial backing of manufacturer Matthew Boulton. Boulton and Watt began commercial production in 1776. By 1800, they had installed 496 engines across Britain and exported designs to France, Germany, and the American Eastern Seaboard. The numbers that followed were without precedent. Between 1760 and 1840, British coal output increased from 6 million tons per year to 34 million. Iron production increased 12-fold. The population of Manchester grew from 25,000 to 300,000 in a single lifetime. Watt's engine made continuous rotary motion possible, converting the piston stroke into the circular motion of a flywheel. Rotary motion meant the engine could drive a shaft. A shaft could drive multiple machines simultaneously. One engine could power an entire mill floor. The logic of scale now ran in only one direction. Bigger engines required more coal. More coal required deeper mines. Deeper mines required more powerful winding engines and higher boiler pressures. Higher pressures demanded a greater tolerance for the consequences of mechanical failure at the point where machinery interfaced with the bodies of those working below. Boulton once wrote to Watt that he was selling something the world could not do without. He was correct. He did not complete the sentence. What the world could not do without, it would not protect. What it would not protect, it would consume. The colliery winding engine of the 1830s was a beam engine scaled upward by 3 decades of commercial demand. Its boiler was a wrought iron cylinder, 8 to 12 feet in length, fired by a brick furnace burning the lowest grade coal the pit produced, combusted continuously across a 12 to 16-hour working shift. The boiler fed steam at pressures ranging from 4 pounds per square inch in early Watt designs to 40, 50, and in documented cases 60 pounds per square inch in the high-pressure engines Richard Trevithick developed after 1800. Higher pressure meant more power from a smaller engine, lower capital cost, faster return. The pressure vessel was fabricated by hand, iron plates riveted together by teams whose work quality varied considerably between workshops. There was no regulatory standard for boiler construction in Britain until 1882. For 60 years, every boiler in every colliery and foundry was built to whatever standard its manufacturer chose, inspected by no independent authority, and tested, if at all, by the owner's engineer. The winding rope in early decades was hemp, subject to rotting in the damp shaft, capable of snapping under dynamic loads. Wire rope began replacing it in the 1830s in better managed collieries, but transition was slow, driven by cost rather than safety. The cage carried men up and down the shaft, suspended by a simple hook and link attachment. There was no automatic safety device to arrest it if the rope failed. If the rope broke, the cage fell the full depth of the shaft, averaging between 300 and 600 feet in 1840. The engineman could not see the shaft. He operated entirely by signal, by the feel of the engine under his hand, and by experience of how the machine sounded when running correctly. On a 16-hour shift, processing dozens of winding cycles per hour, the margin for inattention was narrow. The consequence of inattention was absolute. The dangers of high-pressure steam were not mysteries. They were documented, witnessed, and in engineering circles openly discussed. What was not formalized into law or enforceable standard was who bore responsibility when failure occurred. The answer, in practice, was always the same. The men below bore it. A boiler explosion was not a gradual event. Pressure built silently and invisibly, monitored by a gauge whose accuracy depended on calibration, and controlled by a safety valve whose opening pressure was, in documented cases, deliberately weighted down by owners who preferred higher pressures than the valve's rated setting allowed. When the vessel failed, it failed completely. The iron plates separated at velocities comparable to artillery shell fragments. The water inside, superheated above its boiling point, flashed immediately to steam, expanding to 1,700 times its liquid volume in milliseconds. The resulting pressure wave demolished the engine house. Fragments of boilerplate were recovered at distances exceeding 300 feet. Men standing within 50 feet had no meaningful chance of survival. Between 1817 and 1850, recorded boiler explosions killed more than 1,000 workers. Parliament debated boiler legislation 6 times between 1817 and 1844. 6 times, the manufacturing interest defeated inspection requirements, arguing regulation was unacceptable interference with property rights. Legislators did not argue boilers were safe. They argued the market would correct dangerous practices, that insurers would refuse negligent operators, that workers would refuse dangerous employment, an argument bearing no relationship to the reality of industrial labor, where a collier's family had no practical means of refusing the only pit within walking distance. Ventilation failure produced a different death, slower, less spectacular, easier to absorb into ordinary colliery accounting. The steam engine managed the winding and pumping that kept ventilation functional. When the engine stopped, fire damp concentrations could reach explosive levels. A single candle was sufficient ignition. The men below could not see the gas. They carried their candles into the darkness as always, trusting the system above them. When that trust was violated, the reckoning came not to the owner, not to Parliament, but to the men in the seam. The collier's day began before light, before any light, in the absolute darkness of a pre-dawn that in northern coalfields arrived at 4 in the morning during winter. The men and boys rose in unheated cottages, dressed in clothes not fully dried from the previous shift, ate whatever the budget permitted, bread, dripping, cold porridge, and walked to the pit mouth in groups, their breath visible in the darkness. Then the men descended. The cage dropped into the shaft at a rate determined by the engineman's management of the steam valve. The men inside stood in silence, watching shaft walls pass in faint candlelight, feeling the cold increase, hearing the engine sounds above diminish and the sounds of the working level grow louder. At the bottom, the main roadways were high enough for a man to walk upright, perhaps 5 feet of clearance. Ventilation doors were opened and closed by trappers, children as young as 5, seated alone in darkness for 12-hour shifts, opening the door when they heard a tub approaching, closing it after. Their world was a single door in absolute darkness. They were paid 4pence a day. Beyond the roadways, the seam workings narrowed to 30 to 36 inches in height. The hewer worked lying on his side, swinging a short-handled pick, cutting the undercut at floor level, then driving wedges to bring the coal down. A skilled hewer could fill 8 to 10 tubs per shift. Each tub weighed approximately 500 pounds. The tubs were moved by hurriers, workers who pushed or dragged them through low passages. Where the passage was too low to crawl efficiently, a leather harness was attached, and the hurrier drove forward on hands and knees with their back pressed against the roof. Medical examinations for the 1842 Royal Commission documented spinal curvature in workers as young as 14, chronic joint degeneration, and respiratory disease from coal dust inhalation. A girl named Patience Kershaw, aged 17, described her working day to Sub-Commissioner Jellinger-Simons with directness the parliamentary record preserved. She worked as a hurrier, 12 hours, in water up to her calves. She was, she said, used to it. That phrase carries more industrial history than a shelf of economic analysis. It describes the complete absorption of human endurance into a system that had no category for suffering, that did not interrupt production. The collier's body was a component, sourced cheaply from surplus agricultural labor, maintained at subsistence by the truck system, replaced when worn out. The steam engine required coal. The coal required bodies. The bodies required nothing the system was prepared to provide beyond the minimum to keep them descending. This was not accident. It was architecture. The storm arrived from the southwest on the afternoon of the 4th of July, 1838. It was not exceptional by the standards of the West Riding of Yorkshire. The men who managed Huskar Colliery had seen such storms before. The pit had operated since 1820. What no one had adequately accounted for was the drift. The Huskar pit accessed its coal seam through a slope drift, an inclined tunnel driven into the hillside at an angle that followed the seam's gradient downward. This drift served as both the main haulage road and the primary means of egress. There was a vertical air shaft for ventilation, but it had no cage and no means of rapid ascent. When the storm broke, the drainage channels on Silkstone Common were overwhelmed within minutes. The volume of water descending toward the workings was later estimated at several thousand gallons per minute. It entered the drift mouth in a continuous torrent, traveling downward at a velocity sufficient to knock a standing man from his feet. Within the drift, 41 workers were present, mostly children between 7 and 17, employed as hurriers and trappers. The water reached them before any warning could be transmitted. The signal rope system was useless against a flood moving faster than a man could run. The banksman saw the water entering the drift mouth and understood immediately. He had no means of stopping it. There was nothing to send down. There was nothing to do. 26 children drowned in the Huskar Colliery drift on the 4th of July, 1838. The youngest was 7 years old. His name was George Birkinshaw. They were found in groupings suggesting they had attempted to move together toward the surface and been overtaken. Several were found with their arms around one another. The recovery took 2 days. The bodies were laid out in the engine house, the same building that housed the winding engine whose operation had defined every hour of their working lives. The coroner's jury returned a verdict of accidental death. No individual was named responsible. The pit closed for 11 days. It then reopened. Queen Victoria, newly crowned and 22 years old, was reported to have wept. The Illustrated London News published engravings. Lord Ashley, Anthony Ashley Cooper, later the 7th Earl of Shaftesbury, had been pursuing reform of child labor in mines for 2 years. Huskar gave him the specific, named, counted evidence that abstract argument had not. In 1840, Ashley secured the Royal Commission on Children's Employment. Its report, published May 1842, contained detailed illustrations of children hauling coal in harnesses and trappers sitting alone in darkness. The Mines Act received royal assent on the 10th of August 1842. It prohibited women and girls underground. It prohibited boys under 10. It established, contested, delayed, imperfectly enforced, but established, that the state held legitimate authority to regulate the conditions under which human bodies were deployed inside the industrial system. 26 children in a Yorkshire engine house had purchased that principle. The Mines Act of 1842 was, in precise legislative terms, a partial correction applied to a system whose fundamental operating logic remained intact. It removed the most visibly objectionable workers from underground, and in doing so gave Parliament sufficient evidence of conscience to absorb the pressure Huskar had generated. The deeper structural questions, absent boiler inspection, no mandatory shaft safety equipment, no enforceable ventilation standards, remained outside its scope. Lord Ashley had proposed mandatory inspection by independent inspectors with genuine enforcement authority. The coal interest defeated this in committee. What emerged was a single mines inspector, H.S. Tremenhere, appointed to cover the entirety of British coal production, hundreds of collieries, tens of thousands of workers, with no power to compel access and no staff beyond himself. Tremenhere filed his first report in 1844. Precise, measured, and entirely ineffectual. The deaths continued, averaging over 1,000 per year between 1843 and 1850. Each legislative step forward was preceded by disaster large enough to overcome the manufacturing interests' resistance. The Hartley Colliery disaster of 1862 killed 204 men by entombment when a single shaft was blocked by a collapsed beam from the winding engine above, producing legislation requiring 2 independent means of egress. A requirement so elementary that its absence is explicable only by the consistent legislative priority of capital cost over worker survival. The workers were not passive. The Miners' Association of Great Britain and Ireland, founded in 1842, reached 70,000 members within 2 years. It collapsed in 1848 under owner offensive and legal suppression. It was rebuilt. It was always rebuilt, because those men understood what parliamentary debates consistently failed to articulate. The engine needed them more than they needed the engine. Without their bodies in the seam, the coal did not move. Without the coal, the furnaces went cold. Without the furnaces, the empire did not hold. The collier was the first link in a chain, ending at the counting houses of the City of London. The least protected link. The most essential. That contradiction, indispensable and disposable, was not an oversight. It was the operating principle. The last deep coal mine in Britain closed on the 18th of December 2015. Kellingly Colliery, in North Yorkshire, 40 miles from Silkstone, wound its final cage to the surface at the end of a morning shift. The men who rode that cage had worked the same seams, above the same carboniferous rock as the hurriers and trappers of the 1830s. They rode in an enclosed steel cage with safety catches and emergency communications, protected by legislation whose foundational logic traced back to the disasters that had made regulation politically unavoidable. They were the last. The intervening 177 years produced an estimated 100,000 deaths in British coal mines. The true figure is higher. How much higher, no methodology can now determine. Britain's Industrial Revolution produced the most dramatic expansion of material wealth in human history to that point. Between 1760 and 1900, real GDP per capita increased by a factor of approximately 4. Life expectancy rose from 37 years to 51. Literacy rates climbed from 40% to 97. These are real gains. They belong in the accounting. So does everything else. The 100,000 dead. The uncounted thousands killed by boiler explosions, by occupational lung diseases, pneumoconiosis, silicosis, the black lung that settled into the tissue of men who spent 30 years breathing coal dust. The children whose spines curved permanently before their bones had finished forming. James Watt died in 1819, wealthy and celebrated. The watt, standard unit of power, ensures his name appears in every physics classroom and engineering calculation in the world. The names of the 26 children of Silkstone are recorded in St. Mary's Church Parish Register, buried in a grave that still exists, still visited, bearing the inscription cut into stone in 1838. The steam engine did not act with malice. It was a mechanism, iron, water, and fire, converting thermal energy into mechanical work. It did not choose its operators. It did not write the legislation governing its use. It did not determine the age at which children could be sent into the shafts it served. Human beings made those choices. Human beings voted 6 times against boiler inspection. Human beings weighted down safety valves. Human beings employed 7-year-olds to sit alone in darkness for 12 hours and entered the wage cost in ledgers that survive intact in county archives, available to anyone with the inclination to look. The inclination to look is the minimum that history requires. Not guilt. Not nostalgia for a pre-industrial past that was itself brutal. Not a simple narrative of villains and victims. What history requires is the complete ledger, the engine that pumped floodwater from deep seams, the engine that drove the mills that clothed a continent, the engine that pulled the first locomotives across the English Midlands. This engine is also the engine that stood above the drift mouth at Huskar Colliery on the 4th of July 1838, turning its drum, maintaining its pressure, performing its function without interruption while the water rose. Below it, and 26 children ran toward a surface they did not reach. Both things are true. The complete history holds both without resolving the tension between them, because that tension is not a problem to be solved. It is the accurate description of what industrial civilization is, how it was built, and what it continues to cost in the mines of Shanxi province, in the garment factories of Dhaka, in the supply chains of every economy that has inherited the operational logic of the system that Watt's separate. Condenser made possible on a Sunday morning in Glasgow in 1765. The engine still runs. The question of who pays for its running has never been finally answered. It remains open. It remains ours.